Welcome everyone. Today's topic is the thermoelectric cooling or Peltier cooling. I would like to talk about this because I saw many videos in the internet on YouTube, and I saw that many people are messing up these things, and they don't understand how these devices work. So I want to make it clear, or I try to make it clear how they work, and hopefully that will be useful for those people who cannot understand the basic principles of these devices. So basically, a thermoelectric element is making a relationship between thermal processes. So let me write it down. Which can be heating and cooling, and electricity. So this basically means that if you have a gradient in temperature, that will produce some electricity. Let's make it like this. Or if you have a gradient in electricity, now I just make it like this, or to be more precise, if you have a current flowing, that will induce a gradient in temperature. It's more like this. This is not so good. So if there is a current flowing in the current, that will induce a gradient in the temperature, or if you have a gradient in temperature within your circuit, that will induce a change in the voltage of your current of your circuit. So there are basically two devices which use these things. So the first is, if you have a gradient in temperature and you have a voltage change as an output, that will be a thermocouple which uses this phenomenon. So basically you have two different metals joined together, and you can measure the temperature with this device. And then if you want to use the other type of process where you introduce current and get a temperature gradient, that is the Peltier element. Let's call it Peltier device. So you have a power supply, you have this small block which you can buy from the internet, you connect it to your device, your power supply, and you will have one side of this device getting warmer and the other side will get cooler. So what is the science behind this? So the science behind this is the following. So I said that you have different materials joined together. So let me draw a simple sketch. So let's make it like this. So we have a block of material B, and then let me just draw something just to make it more simple. And then this is A, and this is also A, so this is the same material. And then let's put this into an electric circuit. So this is basically a battery or a power supply, whatever, plus, minus. So this point of the circuit is T0, and then we have U0 at this moment. And then let's say that this point of the circuit is TH, H stands for hot, and then this point of the circuit is TC, C stands for cold. So this is basically the whole stuff here, and you have a current I flowing in this direction. So let's have some discussion. So the circled areas are isothermic, and then we can define the resistance of the whole circuit as RAB, and then there are two processes. You have reversible processes and you have irreversible processes going on when the current is flowing through your circuit. So what is what? If you have reversible, those are the following. So you have ZPak Effect, you have Peltier Effect, and you have Thomson Effect. So these are effects. And then what is irreversible? So you have heat conduction and also you have the Joule heating. So if you have current running through the circuit, then these 5 effects occur. So I would like to go through these effects one by one and explain them, how they affect your Peltier device and how you can improve your device. So I listed 5 effects. Let's start with the irreversible ones, and let's start with the Joule heating. So what you have is that you have an I current in your circuit that will produce a Q heat, because you have a resistance, and in this case your Peltier element is the resistance. So if you run current through it, it will get warmer. It's like when you just grab a piece of wire, you connect it to a power supply, and if you apply current on the wire, then the wire will get warm. So basically the heat equation looks like this. So as you can see, this is the heat and this is the time. So dq over dt equals R times I squared. So you can see that the Joule heat is a quadratic function of the current. So it can raise quite strongly with raising or increasing current. And this is a huge thing. So this was the number 1. And then the second is another irreversible process during the operation of the device, is the heat conduction. How this happens? So if you have different temperatures, in this case you have your Peltier device and you have a warm and a cold side. So if you have this difference between the two sides, that will induce a heat flow from the warm part towards the cold part. So that means that so you have a temperature difference, and that will induce heat flow from hot towards cold, and it's always like that. So if you have like a surface area, because the heat is flowing through a unit surface area, let's say, then the change of the heat in a unit time is like you have the heat conduction coefficient and then dt over dx. So this is another loss. So despite that you have a cold and a hot part, they are not independent from each other in a Peltier device. So you have to consider that. and the more hot you get on the hot side, the higher is this effect. And then we can go through the 3 reversible effects. The first one is the ZPak effect. And basically this is how we can understand the main the main principle of these kind of devices like Peltier device and thermocouples. So what you have is, this is mainly for thermocouples, just thermocouples like this. So if you have a temperature gradient, so that will cause an inhomogeneous electron density. Let me write it down. So inhomogeneous electron density in the material, and if you have inhomogeneous electron density, that will induce an electric field E. And then this electric field is proportional to the temperature gradient, and this proportion can be expressed like this. So it's something like this. So you have the electric field, and that is basically equivalent with the ZPak coefficient times the gradient of the temperature. So this is basically the equation. So how it looks like, let's say you have this block of your material. There is no current flowing through your material, so let's fix I to 0, and you have T1 and T2 temperature, and let's say that this is the hot side and this is the cold side. So therefore you will have a field like this. So you have just a few electrons here. This is I mean, it's not the reality, so not this much few, but you can understand. And you have more and more, and yeah, this is more and more denser. So the density increases in this direction. So this is how you can understand. So you see that there is a temperature gradient, and then there is a gradient in the field as well. And if you have a field, then you will have a voltage as well. So this is how you can understand. So this was the third effect, but I want you to understand this better. So ZPak effect. Let me draw this again. So we have a block here, and there is no current. There are two temperatures, and you have the hot and cold, and you have the electric field like this. So now let's draw the other guy again. So this was material B, and then let's make it like this. So this was material A and also material A. So you connect them to a power supply, whatever. And then this is T0. And then let's call this TH. And let's call this TC. So 0 cold, hot. So actually you can formulate this with mathematical formulas. So we say that we connect these different materials, and even at U0 equals 0, so at U0 equals 0, you can measure, one can measure voltage. So you don't apply any power to the power supply, and there should not be anything happening here, but since you connected different materials, you will be able to measure voltage on this circuit. So basically what we say that we can get this through or across 2 points by integrating the electric field, and then we can like split up this equation to the different parts here. So let's do that. So basically the 2 points is you will see it from the equation, but what we have, so first we go from P1 to PH, so from here to here, and we have the A materials ZPak coefficient, and we have a gradient in temperature. So we integrate this first, plus I write a new line. So we are at the pH, so here, and we go to the PC, and then we go through the B materials, so we use its ZPak coefficient. So then we move from the TC to the P2, so like this, and we went through the A material. Like this, and we can just continue with these equations by expressing the gradient of the temperature. It's very simple. So first is SA, and we have T hot minus the T0, so this gradient here. And then we can move on to the B, and we had the cold and the hot gradient, so this gradient here, and then finally we go back, so we had a gradient between these 2 points. And then this can be, you can work yourself through the parentheses here and simplify the equation, so you will end up with this formula. So you use the ZPak coefficient, the combined ZPak coefficient, which is basically SA minus SB. So this is the system's coefficient. So use that and the gradient between the TH and TC. So T0 actually gets cancelled out from the equation. So you can get the voltage. And then this gives us a very nice like equation to measure the SAB. So we can actually measure this guy. So if we say that SAB, which is a function of temperature, of course, can be measured through the DUAB DTM, and the cold should be constant. So actually you can measure your Peltier device's ZPak coefficient by keeping the cold or the warm side, actually keeping the warm side at a constant temperature, and then measuring the change in the output voltage and the temperature of the cold side. So for example, you cool down your device to -20 degrees, then you switch off the power supply and then start to measure the output voltage from your device, and at the same time you measure the temperature, and you will be able to plot this. So you can plot the temperature versus the voltage, and from that you can get back the ZPak coefficient of your circuit. So this is a very important parameter. Basically this describes your device. So I think we can move on to the next issue. So you have a circuit made of two different conductors. If there is a current flowing through the circuit, depending on the direction of the current, so the polarity, one point of this circuit will be cold and the other circuit will be warm. So the Peltier effect is actually used for the Peltier devices, so for your thermoelectric cooler. So let me draw it, and it's more simple to understand. So you have a like this. So this is basically the same device as I showed you previously, but now I draw it like this. And then you have an I current flowing through your circuit, let's say. So we can formulate my previous sentences. So the change of heat is basically the Peltier coefficient times the current. And you should notice that this is a linear function of the current as compared to the Joule coefficient, Joule effect or Joule heating, which was I squared. And then, so this is the Peltier coefficient. It's usually measured in volts, and basically PAB equals PA minus PB. But what happens here? So, because this is a very nice physical phenomenon, so I want to tell you how it works. So, in the material, or in different materials, the electrons have their own chemical potential. So let's say in the A material, the electrons have mu A chemical potential, and here mu B, and then mu A. So in different materials like A and B, the electrons have different chemical potential, mu A, mu B. So if there is a current, then what happens first, that the electrons from the A material, let's call them EA, so E stands for electrons and A is that they are originated from here. So the EA electrons go to the B materials field. So let's just so let's say that A electrons had some energy, and then in the B field, the electrons have higher energy, or should have higher energy. So that means that where they were here, they had some kind of energy, but when they are in this region, they should have higher energy. That means that they have to pick up energy, and how they pick up energy is like they get it from the material, so get it from the lattice vibrations, for example, and that is basically like you are in the A material, let's say this is the energy, and then suddenly you are at the you are at the B, so the electron energy will be like this. So at this point you get energy for the electrons from the materials. That means that the material will cool down at this point. So at point 1 material cools down, and let me go through again. So in the A material you had mu A chemical potential, and in the B material you have mu B chemical potential. And this is basically when these electrons go to the or feel the field of the B material, which is higher than the A. They should also increase their energy, so they will change their chemical potential to B, and that will happen through getting energy from the material itself. So therefore that will cause the material to cool down, because it has to get the electrons have to get their energy from the material, and then the electrons are in the B material, and now they are about to get back to the same A material, where they have to have, or they have lower, because the chemical potential in the A for them is lower, so they have to go back. And then this energy is basically the electrons lose their energy, and how they lose their energy is basically giving it to the lattice or giving it to the material, and that will warm up the material. So when we are at the point number 2, material warms up. So I don't know if I made it clear, but if you have transition from A to B, and we also say that mu A is lower than mu B, then there is a cooling, and then if you have B to A and we have the same, then you have warming. So the material cools down, and here it's getting heated up. So this is how the Peltier effect works, and this is the principle what we use in the Peltier device. And then finally we have our 5th effect, and this is the Thomson effect, which is basically if you have a material with inhomogeneous temperature when the current is flowing through the material, then heat is being produced. So you have inhomogeneous temperature while the circuit is on, basically, while I is not 0, then there is a heat flow. So basically the heat flow can be described with the following equation. So you have the Thomson coefficient here times the I, and of course it has to go through the material. But this is not important, it's negligible. So basically I think these are the 5 effects what I told you, just to refresh. So the first is an irreversible, you have the Joule heating, and then another irreversible is the heat conduction, so these are irreversible. And then you have 3 is the Peltier effect, and then you have the ZPak effect, and you finally have this recently discussed Thomson effect, and these are reversible effects. And also you should see that these are basically the counterparts of each other. So either you change the temperature, so you induce a gradient in temperature, or you induce a current in your circuit, then either you have a ZPak or Peltier effect. So these are the working principles of a Peltier device. So I made this sketch to understand the device better. So basically what is inside the device is you have a conductor layer, which is this and this. These are usually made of copper, and you have A, B, A, B, A, B. These are different semiconductors. I think one of them is like tin and bismuth, so that is how they work. And then these blue and red rectangles are usually some kind of ceramic. So you have this semiconductor sandwiched in between 2 ceramic plates, and that's what you touch when you hold your device, the ceramic plates. So if you induce a current, then you will experience that one of the sides of this device will be cold and the other part of the device will be hot. So T0 is now here is the cold side, and the TH is the hot side. But people usually use this device for cooling, and what they do is basically they take the hot side, they apply some cooling on it, either by air or water, and they try to keep it at a constant temperature, and then you have the cold side of the Peltier device, and that will do the cooling part. So let me explain further how this works. So what happens? You can basically divide the effects into like 2 parts. So let's say you have a balance. So you have a heat from the Peltier effect, which is basically like this, if you remember the equation. And then you have a Joule heating due to the resistance of this semiconductor sandwich and the applied current. you also have a heat, which is basically QC, let's call it, that is the heat conduction, or so you have a heat conduction coefficient, or heat loss can be also said for this. So you have the heat, the temperature gradient between the T0 and the TH part, basically. And then let's call it just dq. This is the heat loss towards the environment, because you expose it to the environment. So then we can put together this. So the heat which is pumped out from the cold part of this device can be described with the following equation. So this is the heat at each time, let's say. So you have the Peltier heat, and then you have the Joule heating, and then this is also D, sorry, and then this is the from the environment, or not from the environment, from within the Peltier unit. You have the heat conduction, so that's QC, and then you have the environment as well, like, and then you can just go and substitute the things from above here. So this, and then well, maybe this minus and plus should be the other way around, but now we can see that, yeah. So this is what we have, and we lose everything because of these other things. So we could see that we have the Peltier here, the Peltier effect, and then this basically is dQp dt, which equals with I times the ZPak coefficient of the device times the temperature, and then that is basically this guy here. And we saw that this is the Joule heating, and then we saw that this is the heat conduction inside the device. So you have the warm part and the cold part, and of course the heat goes from the warm to the cold, and that will warm the device itself. And then environment. So in theory you can do some stuff which, or in theory you should consider some things which can improve your efficiency of your Peltier device. So first of all, you have to consider the current, right? So you have to choose the proper current in order to be able to cool down your device, because if you use too high current, due to this quadratic term, you will overcome this linear term, and then instead of cooling, you will heat up your device just by running too high current through it. Then you have this as well, this term. You should cool your device properly, so you should keep it at room temperature or near room temperature as much as possible, because if the hot side, which you try to cool, is too hot, then a lot of heat is leaking to the cold part, and then you will warm it up. And this is now the second term, so you are fighting against the Joule heating, and then you have the heat leakage from the hot part, so you should keep it cold. And water cooling, and then you have heat loss. This is insignificant as compared to the other two, but you should use some kind of insulating material. So you should make a small styrofoam case or something which is very bad at heat conduction, and you should use your device there, and therefore you will be able to cool it down properly. But I will have a coming video where I will show you everything in practice, and I will explain everything in practice based on the contents of this video. But still, I hope that this was useful enough and I haven't really confused you. But if you have any questions, just let me know in the comments, and see you in the next video where I will explain the theory in practice. So see you there.